Okay, great. Welcome everyone to the SOPA CFD seminar. It's a pleasure to introduce today's speaker, Sloane Wiktorowicz, who comes to us from UC Santa Cruz, where he's an assistant research astronomer. Before that, for 3 years, he was a NASA Sagan Fellow with Greg Laughlin. And before that, for 3 years, he was a postdoc with James Graham and Paul Callis at Berkeley. And before that, he was a graduate student with Sri Kulkarni at Caltech. And he tells me, although I don't know if I believe him, that years ago I corrupted him in 1995 maybe.
I think 6, but yeah.
96, where I allowed him to command a 145-ton Lick 3-meter telescope as a high school student. And I was observing, and I must have broken all sorts of laws, but
you're still here, not in jail. So.
Yeah, so don't tell anyone. Okay, so I'll leave it to Sloane Wiktorowicz.
Thank you. So I'm very excited to talk to you about ground-based study of the atmospheres of planets around other stars through the use of new instrumentation. So briefly, I'll talk about my approach to developing instruments. I'll dive into exoplanets. I'll show you how we're not limited by photon noise from planets around other stars. We're primarily limited by instrumental and telescope systematic effects. So these are non-random effects that don't attenuate with 1 over square root time. So then I'll dive into the instrument that I developed, which is a scattered light polarimeter, Polish 2, you asked earlier about. It's a visible light polarimeter to observe scattered light from exoplanets, so light reflecting off of their atmospheres. And then I'll propose an instrument, a ground-based photometer with space-like quality that I think we can develop. And finally, I'll show a slide about non-exoplanet science that can be done. When you develop a new instrument, it tends to be the case that it is amenable towards other kinds of science that you didn't necessarily think of originally. And then I'll conclude. So my approach to instrumentation is science first. So the goal is to define the science that will transform your subfield. From there, the idea is to look at the right technique, the right photon properties, so amplitude, phase, wavelength, polarization, to try and enable the science that you defined above. And then you look around to see the facilities that you have access to and see where the limitations are and what is preventing you from achieving that science, that high-level science that you want to do. And from there, you'll get a better understanding of how you can improve new instrumentation to get you the science that you want. This involves a lot of processes, such as constructing, commissioning, and calibrating the instrument. And so let's dive into exoplanets, because that's my main area of focus. So it's been said that the status of exoplanet science nowadays is about where solar system planetary science was about 50 years ago. And I think that's mostly wrong for the following reasons. So here is an image of Jupiter from a very nice amateur telescope. And you can see right away that there are some things on it that are interesting. You can see the Great Red Spot, you can see bands, you can see the shadow of a moon. By the way, you can tell that solar system planets have moons. We don't know of any moons around exoplanets. And it's almost worth going without saying, because we're looking in scattered light here. Now, this is fairly obvious because our eyes are adapted to visible light, so we're seeing the light that's reflecting off of the planet from the sun. Now, the state of exoplanet science is this is essentially the current state of the art of exoplanet science, where up here I'm showing an image of a star tens of light years away, maybe even 100 light years away, that has 4 known planets around it that are about 7 Jupiter masses. So these are very massive, young planets that have been directly imaged. So this is an actual image of these planets with the star subtracted out in order to show these planets. Now these planets are point sources, so they're not this nice, beautiful disk like we see for Jupiter. So right away, exoplanet science is at a disadvantage with respect to solar system planetary science. The other type of planet we've been looking at recently are spatially unresolvable planets. So these are planets that they orbit so close to their host stars that you're never going to separate out the star and planet in an image. They're just way too close. You can't build a telescope big enough to do that. And so we rely on light curves. So change in intensity with time, that tells you not only the presence of the planet, but can give you some handle on the atmosphere. But again, these data for exoplanets are dominated by thermal emission. We're looking at black body or roughly black body emission from these planets. we really want to see them in scattered light as well, because that tells you some interesting things about them. So I'll get into scattered light later. So to show this main planet here that's been observed with the Spitzer Space Telescope, this is a well-known transiting exoplanet that has a telephone number with that I won't bore you with. But it's a Jupiter mass, and it orbits in 2.2 days. We don't have anything like that in our solar system. And so this is highly processed data from the Spitzer Space Telescope showing essentially intensity as a function of time throughout the planet's orbit. The planet transits, so its orbital geometry is favorable so that we see the planet go in front of the host star every 2.2 days. And that's indicated here. So that the planet goes in front of the star, you block 1% of the light, which flies way off the screen here. But then half an orbital period later, the planet goes behind the star. And this is in thermal emission. So what that means is you're seeing thermal radiation from the planet that is blocked by the star just because of geometric effects. And that tells you that the amount of flux coming from the planet is this amplitude. You can measure photons that originated from the planet. This is in thermal emission. So let's look at the noise properties here of this highly processed image. So right here I'm showing an estimate of what I'd call the sensitivity, which is, I would say, essentially the ability to measure a change. So if you're looking at this system for a certain amount of time, if you see a signal that has an amplitude larger than the scatter here, you've measured a change in something. Right? You've measured a change in the planet or the star or your instrument or whatever, but you've measured a change that's not due to photon noise. And so this sensitivity value, it's due to photon noise. It's random, normally distributed noise, which means that it'll attenuate as 1 over square root time. You observe 4 times longer, you'll get twice as good data. Now, what you really are interested in astrophysics is not necessarily sensitivity, but accuracy, because you want to be able to make some scientific claim about what's happening. And I would put forth that the difference between sensitivity and accuracy is that accuracy is a way of throwing out changes that aren't due to your science topic. And these will not attenuate as 1 over square root time. That's important. For an example here is, you can see as the planet goes behind the star, and there's thermal emission from the planet that's blocked, so you see the fact that the planet was there. But then right afterward, look at this blip right here. This is significant because the sensitivity of the instrument is given by the photon noise here. It's the amplitude right here. And you can see this peak-to-peak variation is larger than the photon noise. So the instrument is sensitive to these changes. But what we really want to know is what caused this change. And we have no idea. Actually, we do. It's probably the instrument. It's probably not the planet, probably not the star. But if you're trying to understand what's going on in the planet at this level, at the sensitivity level, the photon noise level, you really have to know what your instrument is doing to cause these. You can't just sweep them under the rug. So this is a hint that maybe if we want to study planets with very high accuracy, not sensitivity, we really need to develop instruments that have low systematic effects. We really need to start understanding our instruments better so that we can make science claims that we want to make. So again, here's highly processed data. That's not what the data looked like from the telescope. This is what the data looked like from the telescope. So there's a lot of work that was done just to get to this point. And we still have effects that we don't understand. So here you can see the amplitude in the scale bar is 0.1%. The raw data are at 10 times worse. So there's a lot of work that's been done mitigating systematic effects, mitigating the fact that the instrument, the detector, has this sawtooth variation, mitigating the fact that there's offsets in time. So here's that transit that used to fly down under the board. Now in raw data is, you can tell that's there, but you can't see the occultation here. So we really need to be able to understand our instruments in order to make the science cases that we want to make. So I'm interested primarily, or recently I've been interested primarily in detecting planets in scattered light. So looking at known planets, and instead of looking at them in thermal emission, I've been interested in observing the light that's scattering off their atmospheres. Why would you want to do that? There's a lot of interesting science that you can do in scattered light. Just like for Venus in our solar system, you can start to study clouds. in planets. We know certain planets have clouds, certain ones do not. Not just solar system planets, but also exoplanets, planets around other stars. There's a planet here that seems to have some evidence for clouds. There are other planets that have evidence for hazes. So Titan, for instance, certainly has hazes. We can see those with our probes. So when you study objects in scattered light, you can understand or at least measure the existence, determine the existence of clouds, which planets have them, which don't. And in scattered light, there's a possibility of determining the chemical composition of those cloud particles. So in scattered light, you can also probe the differences between different kinds of planetary-like objects. So going from brown dwarfs all the way down to very low mass, few Earth mass planets. These planets in our solar system that fall in these sorts of categories, they all look different in scattered light. So it would be very interesting to observe other planets around other stars that have a much wider variety in masses and observe them in scattered light. Another thing you can do is start to probe the fact that some planets cannot be spherical, or at least the scattering surfaces cannot be spherical. There's at least one planet that seems to have hydrogen escaping from the atmosphere, and it's not completely clear whether that's escape off to orbit the star or that the gas is confined by the planetary magnetic field. So by looking in scattered reflected light, you can start to understand these processes. There are planets that are tidally prolate because they're so close to their host stars that the star's gravity is causing them to be triaxial ellipsoidal in nature. They are not spherical. There are a few examples of Mercury-like planets, maybe lower mass than Mercury, that seem to be ablating away because they're so close to their host star. The flux, the insulation onto the planet is driving out their rocky material into potentially a comet-like tail. That would be potentially visible in scattered light. It'd be very exciting. And by the way, we've been observing transiting planets primarily. We've been observing atmospheres from transiting planets. That is, these planets that have their viewing geometry just so that we can observe the planet go in front of the star. But the probability of a planet transiting is not great. So most of the radial velocity discovered planets we know about are not in transiting geometries, and we've essentially not been able to study them because we don't know how. So looking in scattered light is a way of observing these planets. That's sort of what you can do with a 10-meter class telescope and a specialized instrument. If you go to something like the 30-meter telescope, there's a lot more very interesting science, planetary science essentially, that you could start to do with exoplanets. You can start probing whether they have surfaces, whether they are solid or liquid. We know the giant planets in our solar system all have had some kind of spot of some color at some point or other in the last few decades. And so it's likely that other planets around other stars will not be featureless atmospheres. So if you have a spot on a planet and it orbits, or it rotates as the planet rotates, you can start to get a handle on the rotation period of the planet. You can start to understand some mechanism for how the planet was formed. And finally, there's some evidence that we'll be able to see chlorophyll if we use the right kinds of instruments on the right kinds of telescopes a few decades from now. So the instrument that I've developed is a scattered light polarimeter at the Lick Observatory 3-meter telescope. It was commissioned 4 years ago. I propose to not only move it to Keck Observatory, but also to develop a new instrument for Keck Observatory because I need more photons. And then finally, there's some avenue for building one for this 30-meter telescope. So now, once you know what the science you want to do, scattered light observations of exoplanets, you need to understand what kinds of measurements you need to make. And in scattered light, photons will be polarized. The scattering process will impart a polarization signature, so I built a polarimeter. In order to understand what we're trying to do, I have to introduce Stokes parameters I, Q, U, and V. These are just measurable, just the way we describe our measurement. And so you can see how they're defined up here. It's just electric field orientations. So you have an electric field coming from the star that oscillates in the x and y direction. You have total intensity here, which is given by Stokes I. Q and U are just the linear polarization. That is the preferred orientation of the net electric field coming from the star. And there's another parameter, V, which is circular polarization, which imparts this sort of out-of-phase modulation between the x and y components of the electric field. This is usually 0 for astrophysical objects. So I'm looking in scattered light. Now, polarization is very, very sensitive on the geometry of the scattering process. So you right there have a hint that maybe we can understand what the geometry of the planet orbit is, the inclination of the planet. Does it orbit in the plane of the sky? Do you have a non-transiting face-on orbit? Or do you have a sort of edge-on transiting-like geometry? And these will impart different signatures in polarized light. So polarization is just the measurement of the electric field components of the incident starlight that I showed in the previous slide. It's a vector quantity, at least linear polarization. You have a magnitude and direction. So the magnitude of the polarized light is essentially given by the amount of white you see on the planet. So the white tells you how much light is being scattered by the planetary atmosphere. As the planet orbits in this contrived geometry, you always see half the planet illuminated. So your degree of polarization is constant because you're getting the same, essentially, flux of photons that are net polarized. Whereas if you have a transiting geometry, the planet appears to go through phases like the moon does as seen from Earth. You have full phase, you have quarter phase, you have new phase. The amount of the degree of polarization will go through these sinusoidal swings. Now, this is just the degree of polarization. The position angle of that, the other vector quantity of this measurement, is given by the orientation of these red and blue lines. That is, the position angle of the linear polarization will rotate with time if you have a face-on geometry. You can see here the red is going from vertical to horizontal and back, whereas the position angle doesn't really vary when you have this transiting system. So you get competing effects that are measurable in the polarization from your instrument. And you can tell whether the planet is, what geometry of orbit the planet has. That can give you the mass of the planet, because we know a lower limit on planetary masses from radio velocity discovery data from planets. Yeah?
Yeah, are you looking at the scattered light, broadband scattered?
Broadband scattered light, right, exactly. Yeah, exactly. So another thing you can get, in addition to the inclination of the orbit, you can also get an estimate of the reflectivity of the atmosphere, and also the presence of clouds and hazes. So here again we have degree of polarization as a function of time, and you see the sinusoidal swing. Now here are three different models that show you what the expected polarization should be of the planet. And if you have a clear Rayleigh scattering atmosphere where you have small particles, you'll end up with a very strong polarization at roughly 90-degree scattering angles. This is why the sky is blue. This is why the sky is strongly polarized, Earth's sky. But if you start putting clouds and hazes like we have on a day like today, you have more and more scattering particles. And so the photons will tend to scatter more times before they come back to your telescope. And each time a photon scatters off of a particle, the electric field orientation will randomize. So the net signal that you get back as you increase the number of scattering particles is to decrease the polarization. So if you observe an exoplanet and you know its period, and you know how far away it is from its star, you know the mass, or you know the radius of the planet, if you know what you should see, if you measure an amplitude of your polarized light that's sort of this level, you know there must be some kind of scattering particle there present, not just Rayleigh scattering particles. And the real clincher here are observations of Venus that were done nearly 50 years ago, where polarization is very sensitive to the size, the shape, and the index of refraction of the scattering particle. These are things that are very hard to get with any other measurement. So these are old data from Venus showing the degree of polarization as a function of time, essentially. And you see there's some very complicated bumps and wiggles here, and a lot of data. Each of these little circles represents some data that were taken. So you go to your Mie scattering theory and model the polarization that you expect from particles, and you see that these particles were fit very well by a distribution of scatterers that's 1.05 microns in diameter, index of refraction of 1.44 at 550 nanometers. It's amazing. So you observe this planet many times with different filters in different wavelengths, and you can plot the indices of refraction as a function of wavelength here. You then go to the lab and measure these properties, the index of refraction, for the chemical species that are likely to be in thermodynamic equilibrium, likely to be present in the temperature pressure conditions of the atmosphere. And you see that water vapor does an okay job, but you really need sulfuric acid in order to explain the polarization in scattered light from Venus. This is why we know Venus has sulfuric acid clouds, because of polarimetry. So I'm planning on doing this 40 or 50 years later on extrasolar planets. So here's the instrument that I use, Lick 3-meter telescope. It's a very small specialized instrument that now weighs less than me. I think that's good, but it's also a little bad. So here's a zoom, a blow up of the instrument here. We have the main optics in the system are here. These PEMs are what impart the polarization, so I'll explain that later. But it's a fairly simple optical system as far as telescopes go, especially exoplanet instruments that are observing exoplanets. So there's a filter wheel, like you mentioned. We're looking in broadband. There's a polarizing beam splitter that splits the light into two beams. Some optics here, and the detectors are just photomultiplier tubes. So it's essentially 1930s detectors here. The twist is that we have readout equipment that is modern. So we get up to 500 gigabytes of data on a long winter night. So the key here is this photoelastic modulator. It's essentially a bar of fused silica, a few inches in diameter. And if you put it on a table, it is non-birefringent. That is to say, if you shine light, shine electric field orientations that are random, there's the index of refraction in this optic is constant regardless of the orientation of the electric field going through it. That's a good thing. But it also has the property that when you stress it, when you squeeze it or extend it, it becomes birefringent. So that index of refraction does change as you squeeze this thing. It becomes a wave plate. So what it does is it preferentially retards the electric field oriented 45 degrees from this axis. So I'll show a video of what that means shortly. So if you shone light with a horizontal polarization, horizontal orientation, oscillation of the electric field, versus this weird 45-degree thing, you would see a change in only one of those components. Okay, so the electric field components that are oriented vertically and horizontally are unchanged to very high accuracy. The electric fields that are oriented in this sort of 45-degree slant are modulated as this bar undergoes a resonant oscillation. So what this does is you can see the intensity of light going onto my photomultiplier tubes, my 1930s era technology. The light is sloshing back and forth between these two beams. You can see if you stare at this long enough, light is in one or the other. We recover essentially all the light. So you see the sinusoid-like modulation that's out of phase between the two detectors. That's by design, so you recover all the light. The sum is zero, or the sum is constant, maybe not zero. You can see that this sinusoid is made up of many frequencies. The odd harmonics of the resonant frequency of this bar of fused silica, the resonant frequency is 50 kilohertz. The odd harmonics encode this circular polarization, which usually astrophysically is not interesting, but I'll show you an example at the end of the talk why it is. And then you can see the even harmonics of this resonant frequency encode the linear polarization. So if you have two of these bars of fused silica oriented 45 degrees apart in the plane of the sky, which I do, you can simultaneously describe the entire electric field state of the incident starlight. You get Stokes I, Q, U, and V without rotating anything. There are no moving parts except a filter wheel in this instrument. You can measure the polarization from 100% all the way down to a part per million, 10 to the minus 6 of a change in a part per million, based on the fact that the amplitude of this AC signal, this AC coupled experiment, divided by the mean, the DC offset here, will tell you the polarization. So here, each of these data points represents an observation of a star on a given night. There are bright stars, faint stars, using a 3-meter telescope, using a 1-meter telescope with the same instrument. So up here I'm showing the formal uncertainty in the measurement. So how well did we measure these data? This is the sensitivity. As a function of the number of photons in the measurement. Some stars are brighter than others. And you can see I've plotted the photon noise limit right here, 1 over square root photons. If you want to measure something to a part in 10 to the 6, you need 10 to the 12 photons or more. That's just how the universe works. But you can see that the observations here, they scale with photon statistics. As you observe a brighter star longer, you get better data. That's good. There doesn't seem to be much, this keeps going down. So you can observe very, very bright stars. You can use larger telescopes, and you will get better data. So there's an offset here that's within a factor of 2 of the photon limit. So we're doing fairly well. We can go on sky at some point in the year, look at some star, and the instrument will get me a number that's sensitive to a part per million if I have enough photons. So if you take that curve and compare it with what you expect planets to give you, you can start to see what kinds of planets you should be able to detect. So here, this y-axis now is an estimate of the amplitude of the polarization from a particular planet. That is, what signal do I expect to see from planet blah, as a function of the brightness of the host star. Because remember, we're looking in reflected light, so brighter stars give you brighter planets. Brighter stars, astronomers have decided, are going to be over here with lower values of magnitude. For those who are not astronomers, that's the cultural universe we live in. So you can see that the curve goes backwards from what you saw from the previous slide. But the point is, with the same telescope, if you observe for a certain amount of time, as you observe a brighter star, you'll get higher sensitivity data right here. And each of these represents an estimate of the signal a planet will provide throughout its orbit. So these gray-filled circles are planets that transit in front of their host stars. They happen to line up that we can see the planet go in front of the star once per orbit. You can see they're preferentially around faint stars. That's a selection effect. There are a lot more planets that we know of around brighter stars that do not transit. Those are these white-filled circles here that we essentially ignore right now in astrophysics because we don't really know how to study them. We don't really know how to characterize their atmospheres because they don't transit. The reasons for that we can go into later. But suffice to say, if there is a technique out there that just happens to be sensitive to these planets that don't transit, we immediately increase the number of juicy targets that we can observe. And so this technique, this polarimetry technique, should be equally sensitive to both transiting and non-transiting geometries. So we immediately have more planets we can study here. And if you go to a larger telescope, see right here with the Lick 3 meter, we're right at the edge of the signal to noise that we need in order to describe a confident detection. I propose a Keck instrument that should get us to the photon counts needed to conclusively see these scattered light planets. And then if you go to an even larger telescope, there's even more planets you can observe. So here are Lick Observatory 3 meter data that I've taken on the same planet I showed earlier in the talk, the one that has this sinusoidal change with the transits, and that blip that I said meant the instrument was cranky. This is a very well-known exoplanet around a fairly bright star. It's a Jupiter mass planet that orbits in 2.2 days. Here I'm showing these weird Stokes parameters again, linear polarization. It's a vector quantity. You really need two plots. Here's the degree of polarization, again, the amplitude of the signal that you see, as a function of where the planet is in its orbit. And the takeaway point here is we don't see anything that's a smoking gun for a planet, because the models we can come up with are either in blue or black, and there's some weirdness going on for sure. But the point that I want you to see is we're seeing signals, we're getting accuracies, not sensitivity, accuracy, because these observations were taken from 2011 to 2014, piled together on the same orbital period of the planet. The accuracy we're getting is to 50 parts per million. Now, in context, the Hubble Space Telescope has observed this system in scattered light. It's observed a signal as the planet goes behind the star, not in thermal emission, but in the optical, in scattered light. So there's a drop in the amount of the intensity on the detectors that indicates that HST is seen scattering from this planet. And the amplitude of that is about 100-ish parts per million. So the scale of the problem here is we take HST, the Hubble Space Telescope, bring it down to San Jose, which is the 10th largest city in the country. It's a very, very large million-plus population city. You observe the same object as HST and get the same accuracy. Okay, so we're getting Hubble Space Telescope-like accuracy from the ground, from a fairly modest site, let's say, and a telescope that's only a tiny bit bigger than Hubble. And we're getting accuracies that are competitive. So we're getting to the point where if we have a larger telescope, we should be able to see scattered light from these planets. So another planet that I've been looking at, sorry for the figure, I increased the contrast as much as I could. This is a planet one of those that cannot be, its scattering surface cannot be spherical. It's a Jupiter mass planet that's on a 26-hour orbit, 1.1 days orbital period. This planet goes around its host star. So you can see these are Spitzer thermal emission that I had nothing to do with. They're amazing data. Spitzer thermal emission, as with the previous planet, here's the intensity as a function of where the planet is in its orbit. Here's the transit. here's the occultation, so the planet going in front of, and then behind the host star, with this weird stuff going on in between. Well, that weird stuff is actually consistent with ellipsoidal modulation of the planet. What does that mean? That means the planet is not a spherical body, it's a triaxial ellipsoid, and depending on where it is in its orbit, it presents a different cross-sectional area. So the planet's cross-sectional area changes as seen by Earth, which means the amount of thermal emission changes sinusoidally. So it's evidence that this thing is not presenting a spherical scattering surface. Well, polarization is sensitive to asymmetry in a system. That's why I'm doing this. So what would that look like in polarized light? So I've looked at this system, and I see some very strange effects that seem to be statistically significant, that the size of the data, the error is within the size of the data point. And it doesn't seem to be that well suited with any model. But the amplitude of this observation is not 50 parts per million like the previous plan, it's 2,000. So there's something weird going on here that's strongly polarizing this system. It could very well be the star, it could be some systematic effect with the instrument, but there's evidence that maybe what we're seeing is the fact that this planet is not spherical. Okay, so I'd like to go into a second instrument out of 3. I don't have time for the third instrument. But the second instrument I propose to develop, and that's essentially a space quality photometer, not polarimeter. I swear it's not a polarimeter. I have a polarimeter that I hope with colleagues here that we can deploy a test prototype version at the end of May for ultimate use at this Lick Observatory automated planet finder. It's a dedicated robotic telescope that would be perfect for this. Okay, so why would we want to do this? Conventionally, ground-based photometry is limited to the 1 millimag level, that is, 1 part in 1,000. What we really want, I propose, is 0.1 millimag. We want an order of magnitude better. Because then we can start to study the most common planet in the universe, which are super-Earths. These are Earth-sized planets that the Kepler mission has recently detected that are very, very common around other stars. There may be 2 Earth radii in diameter. We have no analogs in the solar system to help guide our intuition for what these are. So we know that they're out there, and we know roughly that if you measure the radius, so if they're transiting, if you measure the radius, you have a rough constraint on the composition. That is, how much rock, how much hydrogen, helium envelope do these planets have. But it's not a great constraint. You really want not only the radius, but you want the mass, obviously, because that gives you density, bulk density. Well, if you want to measure the mass, traditionally you go to this radial velocity technique. The Doppler shift of the star as the reflex motion of the planet causes it to move in your line of sight. So that can constrain what the mass of a planet is. The problem is these are low-mass planets, and this technique just doesn't work that well for low-mass planets. So another way to do it is by using the times of transit. So we're talking now about transiting-only planets. This is part of the reason why we study transiting planets. Because you can measure the exact time at which the planet transits the host star, and you can see whether it's periodic or what. So if you have pairs of planets, it has been observed that the gravitational perturbations between pairs of planets can cause one planet to transit early and have the other planet transit late. These are called transit timing variations. So here are our data, Kepler mission data for 2 planets. Both of them transit their host star on different periods. If they were the same period, that would be a little difficult to form. You can see this planet C versus planet D. Planet C has times of transit. So what this means is the measured time of transit subtracted from what you would naively expect, assuming just a circular orbit and no perturbers. You can see that sometimes the transit occurs 5 minutes early. Sometimes the transit occurs 5 minutes late. So you need good data, and you need precise timing in order to make these measurements. But if you overlay the 2 plots in your head, you can see that this planet is late when this planet is early, and vice versa. So the times of transit, the sinusoidal variation in the times of transits are anti-correlated. So from that, you can see, well, the amplitude here on this planet is about 5 minutes. The amplitude here is about 2 minutes or so, which means this planet is more massive. So you can constrain what the masses of these planets is based on these variations that you see. Okay, so here's the technique I propose. You take a lens, great. You put it in a telescope beam. You put it where the telescope focus occurs. Okay, so telescopes focus light, that's the point. You put this lens right where the focus is. your stars in the field will give you a nice spot on the lens. Okay, so you'll center up the telescope so you're looking at the exoplanet host star, so the star that has this super-Earth planet. Its spot will line up here. There will be a lot of other stars in the field that happen to be there along for the ride. There, the starlight will come to focus here. Okay, this is a lens, so it has its own focal length. So downstream of this lens, one focal length later, all the light will come together. It won't be in focus, but all the light will essentially be in the same square centimeter or so of real estate. There's a reason for this. So this is a so-called field lens. This is what I use in my instrument. Again, 1900s technology. In polarization, this is what you would get. Each of these stars is essentially unpolarized. Okay? I swear it's not a polarimeter, but there is a twist to it. So when you look at the net beam that comes out of this field lens, it will also be unpolarized. That is, the amplitude of the Y component of the electric field will equal, essentially, that of the X component. So the sum of the electric fields will be 0. You'll have a lot of photons, but an unpolarized beam. If you stick a linear polarizer at the end of this, you're rejecting the photons that oscillate in the vertical direction. Just come along for the ride and assume that that's an interesting thing to do. You can do it. So then downstream at the focal length of this lens, you'll see all the photons have an electric field oscillation in the horizontal direction. So the trick is then you cut a millimeter or 2 diameter circle right at the center, right where the exoplanet host light goes through, and you rotate it 90 degrees. So that means the exoplanet light will be manifested here as vertically oscillating photons. So all the photons down here that oscillate in the vertical direction came from the exoplanet. All the photons that oscillate in the horizontal direction came from stars in the field. Okay, why would we do this? Well, as the planet transits, remember, we're trying to see transits of low-mass planets. So they change the amount of polarization, or the flux that you get from your system. You'll have a little bit fewer photons during the transit. What that means is the intensity, the amplitude of the electric field oscillating in the vertical direction will be attenuated. Okay? You'll lose these photons while these horizontal photons will be unchanged. That is to say, you'll see that the exoplanet has lost some light with respect to the other stars in the field. So instead of having an unpolarized beam, you'll now have a polarized signal. Why would you ever want to do that? The reason is, in photometry, the reason why we haven't discovered these super-Earth planets is because the instruments are not sensitive to them. That's why we had to go to space. That's why the Kepler mission was required to see the most common planet in the universe. So photometers from the ground tend to be limited to the 1 millimag level. That is a part in 10 to the 3 accuracy. But these planets, they give you a signal an order of magnitude lower. So they're in the noise, so you'd never see them from the ground. Well, I propose a way of doing that, of seeing them from the ground. And that's because since photometers are limited to a part in 10 to the 3, they can't observe these planets. We can build polarimeters that are sensitive to a part per million. I showed you some data. So we can get down to a part in a million. So it should be easy, relatively speaking, to see signals at this 0.1 millimag, this 10 to the minus 4 level. We can do this. So here's how. So what we're doing is we're converting this photometric decrease in flux. So as a planet goes in front of the star, the total photometry, total intensity of photons coming from the star decreases. So we're converting that into a polarization effect. So here's the amplitude of the expected polarization as a function of an important quantity, which is how many photons do you get from the exoplanet versus the rest of the field. So if you have a planet that transits with a 1% amplitude in photometry, so it's a Jupiter mass planet, in polarimetry you'll see a 0.5% if you have the same number of photons in the aggregate of the field versus the host star, the exoplanet host. So if you have a brighter exoplanet host star than the other stars in the field, this technique should work. So each of these circled data points represents the expected polarization amplitude through this wacky technique that you would expect during the transit of the planet. And these triangles actually show that of order, the same amount of the same signal should occur for Jupiter-mass planets in occultation, that is, in scattered light. The same thing the Hubble Space Telescope did to show that this planet I showed before has reflected light from it. So if you can get down to the 0.1 millimag level, which is right here, part 10 to the 4, you can start to see not only transits of super-Earth planets, but you can also see scattered light from the ground in a different way. And this dashed line shows, there's data I have on asteroid Vesta that I can't go into due to time constraints. This is doable. This is a 12 sigma detection on a fairly bright asteroid over the course of detection of rotation of the asteroid over 4 hours. So we can get to these accuracies very, very easily. So I propose that we can develop these instruments to do this, and there's quite a bit that can be done from students. So students can contribute to develop, construct, commission, and calibrate these instruments, and there's a lot of projects available. So briefly, I'd like to show some non-exoplanet work that I've done to show that when you develop an instrument, it's suited for other tasks. Yeah. So here are observations of the Crab pulsar, which is a neutron star, the brightest optical pulsar in the sky that we know of. It has a 34 millisecond rotation rate. So just look at the right side due to time. This is degree of polarization in the optical as a function of where the pulsar is in its orbit, well, in its rotation. So you have a neutron star that rotates every 34 milliseconds. So I'm showing you where the signal occurs as a function of where the planet, or the star is in its rotation. So it's been known for a while, it's a pulsar, which means it pulses, yeah. It's been known for a while that there are 2 pulses per rotation of this star. We can see that here in black curves, so our data we see the pulses with our data. We also see that the polarization, linear polarization decreases. But really what I want to show is the detection of circular polarization. We see sinusoidal modulation and circular polarization that's never been seen before. When you have an instrument that's sensitive to things at very high timescales, there are other kinds of science that can be done. So to conclude, instrumentation is what drives transformative science. So we know that exoplanet science is dominated not by photon noise, but by changes in the instrument, so-called systematic effects. So we need to start thinking out of the box to design our instruments to get to higher accuracies. So the first instrument I've developed is a scattered light polarimeter. It's mature at the Lick Observatory. The technique is conducive towards a lot of science, studying clouds, studying differences in atmospheres, etc. So I propose to build another instrument, and that is one that should be conducive towards getting the masses of low-mass planets. And there's a lot of other astrophysics that can be done with instruments that push the boundary. So thanks.
Okay, I think we have plenty of time for questions. Andy?
So, a systematic effect that you can't control, at least directly, is interstellar polarization.
Absolutely.
So, can you say a little bit about how you deal with that?
Sure. So thankfully, interstellar polarization doesn't change on 2-day timescales. It can change on a week or so. Radial scintillation has shown that. But the assumption here is that we know we're studying known planets, so we know the frequency of modulation. So anything that varies on other frequencies is not important. But for other kinds of science, I've looked at, for instance, using this instrument on circumstellar debris disks, for which there will be a lot of dichroic extinction from you to the star that will impart a non-zero polarization vector. So what I've been doing for those science is to look at nearby stars with similar parallax at different wavelengths to try and constrain what the shape of the interstellar polarization is in the vicinity, and it works okay. Yeah, that is a big problem.
So, one of the problems is you don't necessarily know the distances to
That's true. That's absolutely true. Yeah, and that would introduce a large systematic effect. So that directly would inhibit the search for exozodiacal disks around planet-hosting stars, because that would tell you that would interfere with the mean polarization you measure for this planet. Yeah, definitely.
Can you go back to one of your plots of polarization versus phase that you showed?
For the planets?
One of the planets, yeah.
Yeah.
Either one.
Zoom. Okay.
I'm just wondering, it looked at, that's fine.
Okay.
So it looks like, okay. I'm just wondering if you're detecting very one of the plots, it looked like you might be,
Yeah.
and maybe in this one.
Certainly in this one.
Okay, so that's a great example. So your models are they just based on a uniform disk with some assumed polarization percentage?
Right. So the modeling is done by my collaborators at Caltech, and the red is just assuming a featureless disk that's just giving Rayleigh scattering. The black indicates that the night half of the planet has particles condensing, and you have me scattering particles on one hemisphere versus Rayleigh scattering on the other hemisphere. To try and take into account this potential asymmetry, because you should get the same signal at this 0.25 versus 0.75 phase. So at elongation of the planet, it should look the same, unless the planet's not featureless. So the goal is to exactly do that same thing. Have data accuracy, that is to say, your data, the scatter is within the error bars if you have, if you're measuring the same thing. Conversely, if you measure a significant change in your planet as a function of wherever it is in its phase, then you can try and understand what about the atmosphere is causing that.
Follow up on this, I noticed that the models all predict that in the top two panels there,
Yeah.
the models predict that something is going to decrease, and you have a number of significant detections that increase.
Right. So this.
So is there a physical effect that can cause increases in these polarizations?
Well, all that tells you is the orientation of the line of ascending nodes. So the orientation of the exoplanet can have any sort of the plane of the disk of the orbit doesn't have to be oriented east-west in the plane of the sky. It can have any kind of orientation, and that essentially will give you an interplay between the Stokes Q and U. So that would not be a physical effect. That would just be a ground-based observation effect. But what you should see, if you have a transiting planet, if you have an edge-on system, all the data points should either be below or above a line. So a line joined by the data at 0, 0.5, and 1 orbital phase. So if you see half your data on this, up above 0 and half below 0 for a transiting planet, something fishy is going on. So, like this.
Yeah, that's what I was wondering.
This should not happen. Yeah.
So is the problem that you're not estimating your uncertainties properly?
It's very possible.
Okay.
It's very possible that there was some Earth atmospheric effect that, that caused my formal uncertainty on this data point to be wrong. This is an aggregate of data from a couple years, and this is a winter object, so I suspect some of the data points are not valid based on, Earth's atmospheric transparency. So, yeah, this should definitely not happen.
To that end, I was going to ask, like, the example you showed, the HD 18733,
Yeah.
that is a very active K-star.
Yeah.
There are large star spots.
Right.
So I guess the question is, how do you mitigate against that? Do you observe it out of eclipse and try to build some model?
Exactly.
Of what the polarization
Exactly.
should
So I have a bunch of data taken in occultation. So we're looking at an exoplanet, purposely looking when the planet is not visible, because yes, I'm very, very concerned about these systematic effects, these calibration issues. So we have a bunch of data taken during different occultations, and they vary. That's why this error bar is so large, because there's 3 data points, 3 nights of data, where the observations don't quite line up, and that can't be due to the planet. It's either due to the star, the ISM, probably not, Earth's atmosphere, or my instrument. Yeah, so there's definitely work to be done in understanding exactly what's going on. But I'll turn that around and say, yes, this is a very spotted, active, relatively late type star, and the amplitude is in polarization is 50 parts per million. So that's actually fairly reasonable. We're observing in broadband, so the effects of star spots, plages, whatever, are not that significant in broadband. It is what the data are showing.
Just the broadband variability of the stars. I thought it might not be approaching 1%, maybe 10%.
But that's in photometry.
Star.
That's in photometry.
Photometry, but I'm just saying, I would assume the polarization, variations in the polarization.
We'll find out. So I actually did look at a star with similar calcium H and K, similar R index, to try and tease this out. I observed a calibrator star that has the same level of chromospheric variability that is not known to have a planet, and yes, I should show what the amplitude of variability is for that